Hi, welcome back to our continued discussion on geometric series and sequences. Today we're going to focus more on the series part, which remember what a series means. It means that we are going to add some things together. So, if we take a look at the first one, we want to find the sum of the following geometric series. So, from I equals, or n in this case, from 1 to 4, we let n be 1, 2, 3, 4, and we just plug them in. 2 to the first is 2, 2 squared is 4, 2 to the third is 8, and then 2 to the fourth is 16. And we're just going to add all of those together, because remember, that's what the sigma notation means. Sigma means to add, and if you add all those together, we should get 30. So, is there a formula to find a sum of a geometric series? So, yes. How do we find the sum of a geometric series? Now, just like in arithmetic, there are two types. There's infinite and finite. If it's a finite series, it means it will terminate. That means that we're actually going to have an end. For example, this one right here is considered a finite series because we have a finite number of terms, so it ended. And if it's a finite series, it's very easy to do. Here's our geometric series of our sum. A sub 1 is our first term. Remember that. That's our first term. R is our common ratio. And remember, in this case, I is the term number. So our sum is given by this. The first term times 1 minus r to the n over 1 minus r. And if we take a look at the first one here, number 1, we want to find it. So let's think that should be equals. These all should be equals. Okay. Instead of listing out all 12 terms, we can just use our formula. Now, because this is my formula, because this is in my right form right here, remember this is already our geometric series. There's a sub 1. And it already gives me r. So all we have to do is plug into the formula. S equals the first term, 4, 1 minus 0.3 to the n, which is 12 in this case, over 1 minus 0.3. And we're going to use our calculator for this. So if you go step by step, it's not too bad. If I'm going to do the top, 1 minus 0.3 to the 12th, enter, and I divide that. Now I put the bottom in parentheses, 1 minus 0.3. And I'm going to take that answer and multiply it by 4, and we get 5.714. So the total sum, 5.714. Matter of fact, let's take a look at number 2 here. Our rule. Now the difference is, what's our first term here? Well, this right here, because it has the power attached to it, that's our r. So our first term is 1, and our r is 2. So when we plug this in, we're going to get 1 times 1 minus 2 to the 7th over 1 minus 2. And we just type all of that in our calculator. 1 minus 2 to the 7th. I type in the top first, divide that by 1 minus 2, and I get positive. And if you multiply that by 1, it doesn't change anything. We get 127 for our sum. This is the sum. Remember, this is the sum of the first 7 terms of our sequence. It's a summation. So let's take a look at number 3. Okay? Let's take a look at number 3 here. S, we need our first term. Now, what's our first term here? Now, even though, now take a look, it's not I minus 1 this time, but that's okay. We're starting at 0. It kind of takes care of itself. So if you have I, you start at 0. So if the power, and what you start with. If the power is I minus 1, we start with 1. If the power is I, we start with 0. And it means the same thing for us. We use both in calculus, by the way. So my first term, a sub 1, is 5, and my r in this case is 3/5. I just plug it in. 5, 1 minus 3 over 5 to the 40th over 1 minus 3/5. and we just type this in our calculator. 1 minus, now be careful, 3/5 you're going to put in parentheses, to the 40th, and then divide that by 1 minus, again in parentheses, 3/5. Close them up twice, and then you're going to multiply that by 5. Now notice it's 12.4999999. That's basically 12 and a half. So we can write it like so. Alright, so that's if we have a finite. Now if it's infinite, now infinite means it never, should be infinite. If it's infinite, it never ends. It never terminates. It goes on for an on and 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 on. That's what infinite means. It goes on and on and on. And we have a special formula for this one. Again, here is our summation formula. To get the sum, we're going to take the first term and divide it by 1 minus r. And we have a rule here. R has to be less than 1 or greater than -1. And this is because if the absolute value of r is greater than or equal to 1, the series never will get smaller. It keeps growing and growing and growing. So if the ratio is bigger than 1, the series only gets larger over time. Therefore, it never converges. And we're going to talk about that in a few moments. It never converges. And convergence is a very big part of what we're going to be doing next year and part of this homework. So, for number 4, very easy. What's our first term? 5. R is 1/2. So when we set this one up, the sum, if it's infinite, the first term over 5 minus 1/2, which is 5 over 1 1/2, which is just 10. This is a really cool one when we get to applications, by the way. So see if you can try number 5, and then let's take a look at number 6. Now if you notice, number 6 has a splat by it. And the reason for that is this. A is 2, R is 3/2, which is bigger than 1. By our rule, now if you were to solve this one using a formula, you will get an answer. But we got to know, because R is bigger than 3/2, this one does not terminate. Therefore, this one just gets larger and larger and larger. It's a DNE. It does not exist. And let's take a look at what's happening here. Let's compare this with number 4. Now, if we were to expand number 4 here, we would get 5 plus, plug in this, 5/2 multiplied by another 1/2, we would get 5 over 4, 5 over 8, 5 over 16. Notice, it's getting smaller. It gets smaller. As a matter of fact, we say it approaches 0. So my final term is basically 0. So it's at the very end, just having 0 plus 0 plus 0. So it will end eventually. Its sum will end. Okay? Its sum will terminate. Now, look at number 6. Let's expand this one. We would get 2 plus 6 over 4 plus 18 over 8. Notice, it's getting bigger and bigger and bigger. 18 over 8, 54 over 16. It's getting bigger. In other words, this one approaches infinity. And as a result, we say this one, because it approaches 0, this converges. Matter of fact, that's the definition of a series that converges. This one converges, this one diverges. And we're going to talk a lot about that in just a few moments here. Right now, let's see if we can try number 9. Now, number 9, they didn't give us everything here, but the ... means this is an infinite series. It keeps going and going and going. So we need our first term, which is 9. What's R? Easy breezy, just 1/3, right? How did I get to 1/3 there? So my sum is 9 over 1 minus 1/3, which becomes 9 over 2/3. Invert and multiply, And you get, what's that? 9 times 3 is 27 over 2. And this is what it converges to. So if you were to add up all of these numbers to infinity, an infinite number that follow this pattern, your final number would be 27 over 2, 13 halves. Okay? The same thing like number 4 here. If you were to add up 5 plus 5 halves plus 5 fourths plus 5 eighths plus 5 sixteenths plus 5 32nds all the way through an infinite number of terms, you would get 10. And that's how this formula works. So let's take a look at the back here. All right? Some application problems, okay? Now, we're going to take a look more about these in part 2, but one thing I want to set up with you guys right now, we have 2 different formulas going on here. You have your compound formula from earlier this year, and you have your continuous. So let's review those. Compound, remember, to get the amount, it's your initial principal, 1 plus your rate, over the number of computations, compoundings, times n to the nt. Continuous, that's Purdy. To get the amount, it's p to the rt. And when you come to part 2, we're going to take a look at some examples with these, okay? See you soon.